Okay, thanks for coming today to the seminar. This is going to be a presentation fairly unique. It's a group of folks that are local to Boise State and are going to talk about their multidisciplinary research in using DNA to control chromophores to enable quantum computing with molecules. And we're going to hear from several faculty, so they're going to be tag teaming this presentation. So lots of different factors involved here. Little note before we get started, I joined Boise State in 2009 in order to work for this group and helped lay the groundwork for everything you're going to see today, and had a lot of fun and got to work with Jung Hoong and several other faculty, and only a couple of us are here, still here, that have held on and survived, but it's really incredible to see everything that this group has blossomed into and all of the capabilities that they've been able to establish that are some unique facilities present nowhere else in the world. So please, I'll turn it over to Lan, who's going to start the presentation. She's actually remote, and so Olya will be doing the slide coordinating and then transfer it to you. You guys will be passing the mic, so I'll just turn this off for now. So, thank you.
Thank you. Thank you, everyone. I'm sorry I cannot present in person there because I'm currently in Hong Kong. I just landed 6 hours before, but I'm still very happy, and the MSc the school giving us this opportunity to present what the quantum DNA groups are currently working on, and some of our accomplishment for the past, I think, past 10 years. Okay, so my name is Lan Li, and I'm a professor of the Material Science and Engineering, QDNA Group, including several senior researchers and also faculty, include like Cattell, and he will also present today, and Ryan, and Cattell and Ryan both, and from MSc, Olya is from chemistry, and John Hoon, I think quite a lot of you know that, and he's our adjunct chemistry and MSc faculty. Okay, next slide, please. Okay, so Elton, thank you so much and for the fantastic intro. Yeah, so what we targeting is a quantum computing. Why we need a quantum computing, and I think that you heard a lot and from the national news, and definitely quantum computing is one of the top 5 priorities now and in the nation. And the reason that we want to work on quantum computing is because we always are looking for something, you know, the computer can run faster, and then we'll have a larger memory space. And the classical computers is not fast enough or not powerful enough for us to handle the more and more complicated calculation problem. Like, for example, as a material scientist, and then we working on more complicated material system. And then but the classical computer, if you want to do a simulation, and then it probably would take you years or months and then to finish. And then how can we handle those, right, more complicated material problem? And that's why we're looking for some more advanced techniques, and which is a quantum computer. So and the quantum computer, I want to say just one simple overview would say how can we use a quantum computer is that we use the physical phenomena of the superposition, entanglement, and interference to execute quantum circuits. But nowadays the challenge for that is that you have to make sure, right, the material or your quantum chips and can operate as to implement those the quantum phenomena. You still can be able to see them, and unfortunately you have to operate them at an extremely low temperature, and then very low noise and humidity condition, and nearly vacuum environment. So that's why if you Google quantum computer, and then you will see, and it's kind of like a huge furnace. And the reason for that is because a lot of cost is go to build this cryogenic, the cooling system to make sure the quantum chips can work. at those extreme environments, and definitely, I mean, have a larger footprint and reliance and on the rare earth element as well. So all those things is not sustainable. So that's why, as a scientist, and then we will think about, do we find a better material to build this a quantum computer at the room temperature? So on the bottom right, and then you see, which is what we use is like Elton called the chromophore, and you can also call it dyes, and which is organic molecule, and which can absorb and emit light. So that's why we call it dye. The CY5 monomer here means in one single dye, and is a very typical one of the typical materials, and we use to implement and such quantum computation. Okay, next slide, please. And for QDNA groups, and this is what the teams and we have like the dye synthesis team, which are led by Oyad, and she will present her work later, and also John Hoons, and John Hoons is leading the DNA constructor team, and I will have a next slide to explain why we need to use the DNA, and Ryan and Cattell, and they will present later, and to and both of them, actually Ryan's and leading the ultra-fast laser spectroscopy, and then Cattell's is leading the single molecule characterization team. And of course, my background, but I think quite a lot of you know that my background is simulation, computational material science, so I'm leading the theory and simulation, and with Professor Bernie Yuk. And so this is actually our QDNA team is a very multidisciplinary. So we have the student and staff and faculty like coming from the 10 different academic disciplines. And next slide, please. And all of us have one overarching goal, is to build a system which could target room temperature quantum computing and the quantum entanglement, and using organic molecular materials. And we also collaborate with those are fantastic external collaborators, including the U.S. Naval Research Labs and a bunch of the university and the company as well. So the bottom figure shows you, and we have a variety, we have a different labs, including the characterization and then the dye synthesis and the computational labs as well. Okay, next, please. Okay, so the next, I think 3 or 4 slides, and will be very, very quick overview to tell you why we think this organic dye molecule could be a potential candidate and for quantum computing. And so back to a little bit of your organic chemistry and the quantum physics is like what we interested in is to generate something, a quantum particle called exciton, and which is an electron hole pair. So on the bottom left, the figure to show you ground state, excited state, and then if you already took the MSc, the 311, and then you know that, and through the photon, which is a light, right? And you can excite the electron, and from the ground state to excited state. So on the right figure show you once the electron and leave the ground state, and then you see it will have a hole right and left and in the ground state. And so this will create the electron and hole pair, which is called exciton. The interesting thing for the dye molecule is that you can actually control where the exciton will excite it to, so that you can through like manipulating the dye molecule orientation. And you can excite it to the higher state or the low energy state. So this is why we are very fascinated, very interested in these materials. Okay, next slide, please. And this is the motivation, the research motivation, we got it back to 1993, the Dr. Scored groups. And so they did some very interesting experiment, and on the like the top left and to show you, so they shine a light on the single molecules, and then the right figure is the absorption spectrum, and which is the y-axis, the extinction coefficient, and then the x-axis to show you the light wave number. So extinction coefficient is to review the ability of the molecule like to absorb light and at a given wavelength. So if they shine light to one single molecule, you see there's just one single black peak. And then if they have like a two molecule and get closer enough to each other around like 0.3 nanometer, and then this peak will split to two. So this is a famous theory called like David Dot splitting. And so the reason we could see this splitting is because, so that will be the because of the delocalized exciton. And then you see, so the bottom figures, and so like if your one is called the H aggregate, so which aggregate means is like two dimolecule, and if you put like align them on top of each other's, and then your electron and actually can be excited to a higher energy state. And then if you align them next to each other, we call it like head to tail, and then the electron will excite to the lower energy state. So that means that like the die distance and also the packing arrangement matters. Okay, next slide, please. So now you may be like questions like, okay, how can you control, right, the die orientation? How can I make sure it will be like step on top of each other or just next to each other, just like what I want? You cannot use a tweezer and then so to kind of like control their orientation. So our group, that's why we introduced the DNA, because the DNA has a self-assembly capability, and then just like showed you on the right figure, we can attach the die molecule at the backbone of the DNA, and then so leverage the DNA self-assembly capability, and then we can control the die distance and also their orientation, and hopefully we can get what the orientation we want, like I showed you on the previous slide, that step on top of each other or next to each other. Okay, next slide. Okay, the next two slides is a little kind of like a equation. So, but I'm not going through those like Hamiltonian. This is more like a quantum theory. So, but I just want to show you the first equation, which is like, we call this is a molecular exciton Hamiltonians. And then I highlight the parameter called J parameter in the green, and also the K parameter, and in the blue. Those are the two key parameter. My QDNA groups, and we try to measure. Why we interested in that? Because a J parameter is to control the exciton hopping. So it means that you generate an exciton from a die molecule, and then how strong they can hop from between the two molecule, and this will be the parameter, and we can measure. And then the next parameter called K parameter, and is the name of that is the exciton interaction energy. So we want like when you generate two exciton and they can interact very strongly, and so that will be very important for us to do some like quantum computations. So next slide, please. Another two major parameters, and then we measures and in our groups, and you will hear a bit more and in the next few minutes. And one is the N, which is the number of the hops. Means that the number of the hops that the exciton can make between the die, which is the N. And then this N is controlled by the J, which is the hopping parameter I just showed you. So on the previous slide, so this is the middle figure, and to show you that we could measure that. And then the right figure is another very important parameter. We call it tau D, and which is the coherent dephasing time, and which our ultra fast laser spectroscopy team and could measure. So this is a control, and how the excitons and can and like the exciton, the computational times. And so, but the one thing and we found is like this this coherent dephasing time is controlled by the temperatures. And because if you can see that on the right figure, if the temperature we go like lower, and then the coherent dephasing time actually can go longer times. But unfortunately, what we want is we want to make sure the time will be long enough at the room temperature. But so far, unfortunately, we found that there's a decaying. So what we try to do is to through the synthesis and also the orientation, controlling the dye orientation, and then we could control those important parameters. Okay, next slide, please. I think that's it from me, and then I'm going to pass to Oya.
I'm Olya Mas. I'm a research assistant professor at chemistry department. I started with QDNA Group as a research scientist 6 years ago, and I've been doing synthesis of those dye molecules, building blocks that we want to use to make materials for quantum computing. So like Lan was talking about, so we want to build a molecular quantum computer. So here is the theoretical design how a gate, a universal quantum gate for a quantum computer would look like. So to build something like that, we would need wires of dye molecules. Those black circles represent dyes. So we want to kind of have a tool and mean to synthesize those molecular dye wires first in order to assemble a gate like that. And so there are like three principal examples how a wire can be can look like. So at the bottom we have dye molecules that directly covalently linked to each other. And so this actually does not work very well for our purposes. So we want them to be a little bit further apart and not conjugated. In organic chemistry, we talk about conjugation systems. So we don't want each dye to be conjugated with the neighboring one. So we can, to avoid a strong conjugation, we can sort of figure out a way to assemble them into a wire using non-covalent van der Waals interactions, or we can covalently link them, but through longer non-conjugating linkers. So in my research group, so we are trying to develop synthetic strategies to make those wires. So the dye molecules that we're inspired of and work with are chlorophylls, like those found in plants and photosynthetic bacteria, algae. Like, for example, this bacteria chlorophyll A from purple bacteria. So we don't isolate them from natural sources. Instead, we synthesize them from scratch. Starting from very small organic molecules, building blocks. So we are using multi-step organic synthesis to build a structure of synthetic chlorophyll. Like, for example, this one is the mimic of bacteria chlorophyll A from the purple bacteria. And you can see in the vial here, it's a purple residue. So it's the same color that a bacteria has. So here I have absorption spectrum just to show how similar, so the absorption of synthetic chlorophyll purple curve, how similar it is to the absorption of the natural chlorophyll. So we can, using synthetic means, can really mimic very closely, so natural molecules. So they have the same optical properties we are looking for. So we want to dye molecules to assemble them into aggregates like dimer, trimer, and beyond. And to do it, so we use DNA, like Lan mentioned. So we covalently attach dye molecules to complementary DNA or oligo strands, so oligos are short DNAs. And so, for example, this bacteria chlorine was attached to single-stranded DNA, and then we assembled a dimer of synthetic bacteria chlorophyll A. And we found that it actually functioned very, very similar to a bacterial chlorophyll dimer in purple bacteria. So plants and photosynthetic bacteria are believed to use quantum behavior to transfer the energy of excitation energy they absorb from sun to the reaction center. So this is something we want to do for our rapid use in molecular quantum computing. And so on this slide, I show a different example of how we want to make assemble a molecular wire. So here we take inspiration from a different photosynthetic pigment. It's bacteria chlorophyll C from green sulfur bacteria. And in that bacteria, there's no protein or other template to assemble natural chlorophylls in a very nice high order aggregate. So it happens just by intermolecular non-covalent interactions like hydrogen bonding and hydrogen bonding and coordination between central magnesium atom and oxygen from a neighboring molecule. So we wanted to synthesize a mimic of bacterial chlorophyll C, which would be much simpler. So we just capped the macrocycle, we replaced the central metal, magnesium for zinc, and we replaced those functional groups here. So hydroxy and this 5-member ring with ketone for 2 acetyl groups. And we just did 2 mimics, and we changed only position of this group at position 13, so acetyl. So in this one, acetyl is placed on diagonal, and in this one on the right, so the acetyls are placed a little bit off diagonal, and we examined so their such properties as self-assembly to assemble into a material we wanted to get. And so this one on the left, so didn't work, so it couldn't assemble. And this one on the right assembled into highly ordered aggregate. So it's an absorption spectrum. So we have like monomer here, but those other bands are indicative of like a dimer, a trimer, and probably even a tetramer, which are sort of this wire-like J aggregates we are looking for. So it's a nice example, first of all, to see how synthetic molecules can mimic so natural molecules and maybe even exceed or advance the property or desired function. And it's also a nice example to see how very subtle change in structure can have a profound effect on the bulk material property. And I would just to mention, like for those aggregates we were working with, besides QDNA, we have been working, we did AFM, so with Corey, so we did XRD, so X-ray diffraction, we characterized them with Genesiran group, so was many other groups and characterization, materials characterization methods involved in those to get insight on the nature of those aggregates. I guess the capabilities, what we do organic synthesis, and we work with DNA as well. So we do bioconjugation, we attach dye molecules covalently to DNA. And so with our collaborators and Quantum DNA Group, we do DNA nanotechnology, advanced spectroscopy, and modeling. So I'm going to pass the microphone to Professor Jin-Hoon Lee.
All right, thank you, Ilya. All right, so I lead what we call the DNA construct synthesis team. And I just have this slide for the audiences who are not familiar with DNA nanotechnology. So all of these structures are nanostructures that people have made using DNA, starting from the seminal work by Paul Rodeman back in 2006. You see smiley face, which has become kind of an iconic structure. And then there are other techniques such as DNA brick, where you can assemble three-dimensional structures where you're literally using DNA strands as if they're Lego blocks. And if you look at the scale bar, so this is basically 100 nanometer. So this smiley face is about 100 nanometers wide. And we don't have a scale bar for this, but this is a DNA spaceship or space shuttle. It should be about 30 nanometers, right? And then these days, people are actually, even mechanical engineers are getting into this field to make functional structures out of DNA, including rotors, cantilevers, so on and so forth. So these are some of the things that you can do with DNA. The reason why we use DNA is DNA nanotechnology is the technique where that allows nanometer scale control of assembling different materials. So this is what we call a holiday junction, which is kind of cross-like the DNA structure composed of only 4 strands. Very simple. This is where we actually started back when we began this project back in 2019, and first paper from Olia by in 2020. So the reason why we use this holiday junction is you can see from these schematics that we can build different types of dye aggregates, right? So we have monomer, dimer, 2 different types of dimers, adjacent and transverse, and tetramer. So as Lan said earlier, we're literally using this DNA as if they're tweezers for placing these dyes in specific locations. And why that's important is based on their distance and orientation, their optical properties completely change. So we need to be able to control their optical properties, their exciton delocalization properties for quantum computing applications. So that's why we're using DNA. There are 2 different, so depending on their orientation, their optical properties vary a lot. 2 kind of extreme examples are what we call the H aggregate, where the dyes are assembling face to face, and J aggregate, where dyes are assembling end to end, and their excitonic properties are very differently. So the dyes that we chose to use turned out they prefer to assemble in an H aggregate. Most of the structures that we used using this DNA template ended up being H aggregate. We actually tried a lot of different combinations of dyes, their structures. So we also kind of incorporated some of the synthetic chemistry to kind of force these dyes to a certain arrangements. So we were able to achieve some J aggregates using those dyes, and eventually we want to assemble these on more sophisticated DNA templates toward functional devices such as photonic wires, excitonic devices, eventually toward a quantum gate. This is one example of more complicated DNA template that we're using. This is a DNA brick, which is a 2D version, not the 3D version where they used to assemble that spaceship. So we have 2 different versions of this 2D DNA brick where we put these dyes. So version 1, the distance between the dyes are about 8 to 9 nanometers, whereas in version 2, the distance is about 4 to 5 nanometers. And you can actually see the change in their optical properties. So when these dyes are, so from this example, we learned that when these dyes are about 9 nanometers apart, they don't really talk to one another, meaning their excitons are not delocalizing. But when we reduce those down to about 4 to 5 nanometers, then they start talking. So we can actually put more dyes, kind of at the end of this green strand to reduce that distance, even to even shorter distance. So this is an example of how a DNA brick nanostructure can be a canvas for basically playing around with their arrangements of the dyes toward certain optical properties that we're after. And then just last slide, this is basically pretty much a brainchild of Bernie Yerke. We actually use a computer kind of simulation code that allows us to indirectly kind of fit the orientation between the dyes. So the way it works is we basically feed the absorption spectrum and the circular dye cohesion spectrum, which is fairly easy to make, and then just feed it to the computer, and then the computer does its thing. It basically spits out these information, right? What's the distance, what's the angle, and also what we call the J parameter, which is a measure of the strength of the exciton delocalization between the dyes. So the core capabilities are design, synthesis, purification, and characterization of DNA nanostructures. So if you want to learn about DNA nanostructures, come and talk to us. And also the care modeling for analyzing the orientation and exciton delocalization information. So with that, I would like to hand over to Keitel.
Hello, everyone. My name is Keitel Cervantes. I am the team lead in the single molecule and super resolution team. I joined in 2020. Before me, there were many people, including Elton, as he mentioned, so perhaps one of the last survivors. Many people that of what was the earlier team, they left the team, or they leave Boise State, or they leave this world. Unfortunately, that was very sad. So this field of research is quite difficult because we need to count single molecules and then get some overall properties in the population. So I have just a couple of slides. I'm going to talk about the synthesis capabilities of our team by showing you examples of what we have achieved here in QDNA, and also what we have achieved in other applications. This is the synthesis slide, and the next one is characterization. So one of the bigger problems in QDNA is that we use DNA to bring together dyes, well-positioned then with nanometric precision, but they don't work like in paper. They do whatever they want. We can tune their chemical properties, and we can guide them, but still they tend to do whatever they want, most of the time. This creates heterogeneity, many degrees of freedom. And the only way to characterize it, because we cannot just look at an ensemble property and get conformations, we need to look at them one by one. So what we do is we use a larger DNA template called DNA origami, and we put our systems in this large template. And this large template is placed on a solid substrate made of glass. So with an optical microscope, we can see the properties of the dye systems that are on the larger template. So we have published about it, and we found some strategies how to orient the molecules in the three-dimensional space by either taking advantage of what is the interaction between the dye and the DNA, or using the linkers that holds that dye to the DNA, pulling them apart. So we can align similarly of how we align a polymer any way we want, right? So we take the ends of a polymer and we align it to the ceiling, to anywhere we want, just by using DNA. So that's what we have done. We have also worked with larger structures. As you have heard about this Holy junction, we can place the Holy junction in the DNA origami structure, and we can control the arms and control the angles between the arms. This is quite neat. And also now we are looking at other applications of our dye systems in combination with plasmonics. For that, we have started some experiments of how to put this DNA origami or metallic mirrors. This is unpublished, but I'm happy that we can put them here. In the past, I also worked with single protein nanoarrays by using DNA origami, make these nanoarrays using focused ion beam lithography, metallic layers. So each of here, in each of these spots, we see some proteins, and each well here is like about 100 or 200 nanometers. We put here GFP molecules. Then also have worked in real-time aptamer biosensing. So I have worked a lot with aptamer. This was a headache to make this system work. I tried many things, but yeah, this worked. And the good thing is this is an off-on sensor. Most of the time you see the biosensors, they start with on state and then they go off, and then you measure, but this creates false positives. Then regarding characterization capabilities, so we do single molecule and super resolution microscopy. So here is an image of what is the super resolution microscopy. So we can reach a 5 nanometer resolution by using this DNA origami. We can place these DNA paint docking sites on the DNA origami, each separated at least 5 nanometers, and we can reconstruct the pattern on the DNA origami. So then, by simply getting the angle of the origami relative to the figure, we know the angle of the origami, and then this origami has a fluorescence molecule. This fluorescence molecule have an orientation in space. The way we capture that orientation of the molecule using a camera is by defocusing the sample, and we get a pattern. This pattern can be modeled, and we can extract the orientation of the molecule. Then, by doing some measurements, we can get the angle of this dipole relative to the camera. So we can get the out-of-plane orientation and the in-plane orientation as it is correlated to the host DNA origami. We know how the molecule is oriented relative to the origami. So we found out in general that these organic dyes, they tend to intercalate with DNA. Of course, there is some wobbling. We started collaborating with people in Washington University in St. Louis to add wobbling to our methods. We're working on that to improve the accuracy of our methodology. So this is a camera-based microscopy. So we also have a custom confocal fluorescence lifetime imaging microscopy, also known as FLIM. We can correlate our super resolution microscopy with FLIM to get the fluorescence lifetimes of single constructs. Here is an image of what is the FLIM. We have many tiny single molecules on the background. We can get the photons out of one of these and then monitor the photons over time and get different fluorescence lifetime decays over time. For instance, the beginning, we have the blue curve for the first 20 seconds, then the next 20 seconds is in green, and then in blue, then the next 20 seconds. So they have different decays. Then if we do this for over the population, so this is a very tedious process, we can reconstruct we can get the population fluorescence lifetime. Here in this example, there are like 256 molecules. It fits quite well, and we get the fluorescence lifetime for this. It's an organic dye is 1.45 nanoseconds. Then this capability allows us to use the photons to do some correlations to determine single photon emitters by photon anti-bunching analysis. Here is an example of that. So we have these capabilities. If you have guys samples, we can measure them, or if you have a molecule that is interesting, we can also put it on DNA origami and have some interesting ideas over it. So thank you very much.
Thank you, Keitel. Hi, everyone. My name is Ryan Pensack. I lead a part of the quantum DNA group that we call the ultrafast laser spectroscopy team. I've a colleague Dr. Daniel Turner, who helps directs a portion of our group, and then we also get assistance from Dr. Paul Davis, who I'm sure you all are very familiar with. So a lot of what the group's been talking about today has been structure and optical properties. Kaital got a little bit into dynamics. And so when we're making these molecular quantum devices or quantum gates, in addition to structure and optical properties, dynamics are critical. So you heard a brief bit about this earlier with Lon with these quantum oscillations. We call them quantum beats. These are what drive a quantum device. And so in fact, it's essentially exciting electron to an excited state, coherently exciting electron to two excited states. These two excited states have two orbitals, and the electron hops back and forth between the orbitals and the material. And so shown here, this equation describes the dependence of this quantum oscillation, the time in which this quantum oscillation exists, relating that actually to the lifetime of the transition. Transitions in materials have both radiative and non-radiative decay rates that are of interest to us. So our first work in the group was founded by a really talented material scientist, John Huff, MSc PhD student, who's recently graduated and gone on to an electro-optical company in Washington State. And so our group, we build optical spectrometers, time-resolved optical spectrometers. Shown here are results characterizing the excited state of a lifetime of an electron in this cyanin compound in its monomeric form, dimeric form, and tetrameric form. And so we consider a dimer and tetramer, some of the smallest, most base level forms of material. So what you can see with these data is that the lifetimes go down precipitously when you form dimers and tetramers of this compound, going from about a nanosecond to tens of picoseconds. What was very interesting at this time, this dispute in the literature is this decrease in lifetime due to increased radiative decay or non-radiative decay. Our work actually conclusively showed it's purely non-radiative. And so since then, we found this effect to be quite problematic in the materials that we work with. And we've also, in collaboration with Professor Janae Siren in chemistry, found that this problem actually applies to other materials when you spontaneously assemble them of relevance to other fields. And so that's a big problem for our community, and we're very excited to publish this year work showing that using rigid dyes and certain DNA scaffolds, we could actually get a lifetime of our dimers that was longer than that of the monomers. And so we've overcome this effect we call aggregation-induced quenching. In collaboration with Professor Lee, we shed insight at a microscopic level in that we found that one dimer actually was somewhat shielded from the solvent and the phosphate backbone of the DNA, which we attributed to this effect of overcoming this quenching effect. These were molecular dynamics simulations. So in addition, Lon, in collaboration with Professor Mass, did calculations, density functional theory calculations to shed insight on this difference dipole moment. Lon had related that to this material property called the biexciton interaction strength. And so the larger the difference dipole moment, the larger the biexciton interaction strength. To put the difference dipole moment into concrete form, it's essentially the extent that an electron transfers in any material when it absorbs light. And so critically, these computations showed that the absorption strength quantified by this parameter, the transition dipole moment, these values are quite large, meaning the molecules absorb strongly, and we can actually increase with certain chemical substituents this difference dipole without sacrificing that property. And so as time-resolved spectroscopists, we're interested, how does these substituents impact the lifetime of these molecules? And so another very talented MSc PhD student, Nicholas Wright, who's in the audience here, one of his first projects and papers was characterizing the site-state lifetime of these squarane compounds. We found as the difference dipole moment increased, the lifetime decreased precipitously. Dr. Caitlin Duncan, she's a postdoctoral researcher in our group, currently attending over Zoom, showed that this effect was less, let's say, disastrous in substituted bacterial chlorophylls that Dr. Oyumas her group had synthesized. And so to present or to produce measured values for this difference dipole moment, our group has built what we call a Stark electroabsorption spectrometer. Shown here is John Huff and Dr. Duncan. This is the setup of this is the scheme of the apparatus. Shown here are the results. We can use mathematical models, mathematical equations to model these data and arrive at values which can be used to benchmark against calculations and or present insights on when we put a substituents on compounds to attach them to DNA, what impact does that have on their electro-optical properties? So in the last few minutes, I'll just briefly go through the core of our work. Recently has been sub 6 femtosecond, 500 nanometer to 800 nanometer spectroscopy to measure these quantum oscillations, their frequency and dephasing decoherence time. And so we apply a method we call two-dimensional electronic spectroscopy. For those familiar with NMR, it's analogous to that, but just using visible light pulses. And so in this measurement, we get two axes, a excitation axis and an emission axis. Shown here is the pulse sequence and the measurement configuration. Happy to show you that in the labs if you're interested. Send me an email after the talk. And so another project that Nick Wright took on was understanding why certain line shapes of certain materials get so narrow. And in certain limits, this can actually inform us on the dephasing time indirectly of the material without directly measuring it. So shown here are absorption spectra of cyanide tetramers. One of them had an absorption line width smaller than that of the monomers. Looking at the 2D spectra, we analyzed their ellipticity. That's just a mathematical way of describing their diagonal anti-diagonal line widths. We found that this special tetramer actually had an ellipticity of 0, which means it has a kind of broadening called homogeneous broadening only. And this is actually ideal for single exciton coherence. And so my last slide before handing off to Lon, we're inspired by this work in 1999 by Nakamura et al., where this was the first measurement of quantum oscillations in a superconducting Josephson junction-based qubit. This forms the basis of most quantum computers today. And so there has been nothing done like that in molecular materials yet. We made a serendipitous discovery a couple years ago of this dimer with ideal optical properties for measuring these quantum oscillations in the materials we make. And so we've been vigorously working towards that, sleeplessly, you might say, over the past several months and getting closer and closer. Due to time, I'll just hand it off to Lon here. Lon, feel free to take over.
Okay, thank you. So Ryan, can you stay there to help me to change the slide? Okay, next slide, please. Okay, I'm going to skip this and the next. Okay, so this is what I want to say is our summary slides, and you can see maybe your questions are how can we really work together, right? But we have like 5 different groups. And so we use firstly theory go first, and then computational modeling also will work with the theory team. And we use AI and machine learning to help us to quickly screen, like find out what dye molecules and will be available. And then we put it into a DNA. And so we use some quantum chemistry and also the molecular dynamic to simulate. And those systems you look at, and like, for example, on the right and the left figures I show it. And those results and will guide the dye synthesis and also the DNA synthesis team. And about the structure, and after we have those system, ready, the material ready, and then the sample will pass to Ryan's team, the ultra-fast laser spectroscopy, and also the Catel's team, the single molecule, to do the characterizations. But from the characterization, we get those like parameter, the key parameter, and then I showed you at the very beginning. We'll go back to the theory and the simulation to guide our prediction. So you see, this is an iterated closed loop to work together, but under the one major topic is to find a material that can work under the room temperature for quantum computations. Okay, last. Okay, this of course such a huge work, and then definitely have to have a huge a group of people to work together, and definitely cannot forget about our great funding agents, the DOE and also ONR and the NSF. I think that's it. Thank you.
Open the floor to questions. I know the students in the seminar class probably have some questions.
Thank you, everyone. That was a great talk. I would like to ask, how many dye molecules are required to be self-assembled into a functional system to achieve quantum computing using molecular excitonics?
Yeah, really good question. Bernie Yerke has excellent theoretical models. Well, let me take this back. If you form a dimer, you can have these quantum oscillations to generate a superposition, which is an ingredient for a quantum device. You also need, OEMS had in her slide, this network of dyes. So Bernie Yerke has worked out the different gates. You have a phase change gates, a controlled knot gate. And I think it's somewhere approaching 100 molecules you would need to put together to form a network of dyes capable of universal quantum computation. But yeah, I would turn your attention to a nice Burke chapter by Bernie Yerke and published in 2023, or simply email him. He's a very nice individual, previously of Bell Labs, and very knowledgeable.
Thank you all for your very impressive talks on very confusing stuff. Appreciate it. How much energy is going into like basic quantum computing that's at that near 0K? Like, what's the energy cost for that, and how much could we save by making this possibility?
Yeah, great question. I could take that, Lon, or do you want to take that? Because I think you had it in one of your slides.
Go for it.
Yeah, so I think there was a conference recently, including quantum computing companies here in Boise, that Bill Knowlton and Lon had attended. Actually, 90% of the cost and energy goes in just cooling current quantum materials. We didn't mention, but actually current quantum materials must be at temperatures colder in outer space. I think Elon Musk actually just made a joke recently about putting them on the darkest craters of the moon or something, which is probably a good idea. But yeah, they function at 25 millikelvin. Our goal actually is not even just room temperature, even 4 Kelvin would be a huge improvement over current quantum computing platforms. The particular materials we work with, though, are amenable to other types of quantum information, science-relevant topics, such as quantum communication, teleportation, and quantum sensing. So these superpositions are very fragile. You can think of it like a spinning coin, only lasts for so long. And so you can gain rich information by initializing your superposition and then reading it out at a later time in terms of chemical processes, biological processes, materials processes.
I want to add one more thing is like our group is taking the two approach to implement this room temperature quantum computing. We do know that when you increase the temperatures, and then those like superpositions, right, like Ryan said, and then entanglement will fade out, it will not like exist for too long. And so what we try to do is like we want to, through manipulating those like the molecules, and then we could make sure the exciton can last as long as they can, and at the same time, and can complete the computation as fast as they can. So those are the two approaches, and we are targeting.
Yeah, I'll add quickly. Our materials are unique. We can actually change this oscillation frequency through chemical synthesis, materials assembly. Other materials generally have a largely fixed oscillation frequency. So a lot of other engineers are trying to increase the decoherence time. We have I guess the simultaneously challenge of increasing both the oscillation frequency and this decoherence time. So blessing and a curse.
Thank you guys for the talk. One question that I've had is, what is the risk, or how do you mitigate like denaturing or decomposing the structures since they're all organic molecules?
I'll leave it to the chemists and material scientists.
Here.
Yeah, that's a good question, you know. So we try to use organic molecules, dyes that are relatively stable. So, you know, they function at, so they can withhold, like, I don't know, they find at room temperature. So DNA melts like stranded DNA melts like 40, right? So we don't expect the material to be at 40 degrees. So our DNA origami has even higher melting temperature. So in terms of DNA and for organic molecules, so they're pretty stable. So we can, they're fine at room temperatures. So they, I think, should be okay. Yeah, right. So we do take inspiration from photosynthesis, and again, like in a photosynthetic antenna, so which is believed to like utilize principles of quantum mechanics and quantum effects. Some of those photosynthetic organisms, they live in quite harsh environments, right? In terms of temperature, it can be very acidic, you know, basic, and so they seem to be fine. And there probably might be some sort of replacement you need to replace them from time to time when we come to the stage where we have this material for quantum. There are organic semiconductors. Many people did not believe in organic semiconductors because of their organic, but you know, they found the application, right? So yeah, thank you.
Okay, well, let's thank all of our speakers one last time.